video is on power and efficiency. Question 1. Define power. Equation units. Power is the rate of work done or rate of energy transfer. Has the units of energy over time, or at an exact moment, it's force times velocity. Has the units of joules over second, or Newton meters over second, or watts. Question 2. Define efficiency. Equation units. Efficiency is useful energy out over actual energy in, or useful power out divided by actual power in. Has no units. It has limits between 0 and 1. Question 3. John, who has a mass of 72 kilograms, climbed from an elevation of 3,100 meters to the summit of Torrey's Peak at 4,300 meters. The hike required 4.8 hours. Calculate the average power supplied. So power is delta W over delta T. It's going to be mg delta H over delta T. So you could see we have delta H. We have delta T. Hours was converted to seconds. Question 4. A windlass raises a 200 kilogram anchor at 3 meters per second. Part A. Calculate the average power required. We're going to use the equation P equals FV. Part B. The motor is 40% efficient. Calculate the size of the engine. So efficiency is P out over P in. We were given efficiency and power out. Power out came from part A. Question 5. In 8 minutes, a conveyor belt whose engine is 40% efficient lifts 160 crates, each having a mass of 30 kilograms. The belt, inclined at 59.49 degrees, results in an elevation increase of 112 meters. The crates start and end at rest. Find the size of the engine required to run this belt. It says find the size of the engine. You might think that's like meters cubed. That just means how much energy is needed or how much power is needed. In this case, it's going to be how much power is needed. So power in is going to be P out over E. P out is going to be mg delta H over delta T. And all of these values we were given, or we know, and we could divide by the efficiency to get the power in. This should say 2.75 times 10 to the 4, not 5, times 10 to the 4. Question 6. Danny, who has a mass of 75 kilograms, is swimming at 2 meters per second. The end is near. In 4 seconds, he accelerates to 14 meters per second to win the gold medal. So he's going to go from 2 meters per second to 14 meters per second. Part A. Calculate the work he did during the 4-second sprints. So work is equal to the change in kinetic energy. And we were given all those values. Part B, calculate the average power during the sprint. So we have delta W from part A. Part C, calculate his acceleration. We were given V initial and V final. And we were given time, 4 seconds. So this is all given to us. Part D, calculate his velocity at 3 seconds into the sprint. So we're going to use the equation V is equal to AT plus U, or V final equals AT plus V initial. Part E, calculate his instantaneous power at 3 seconds. So this is the velocity at 3 seconds, and F is equal to ma. So we know m, we know a. A from part C. Question 7. Paige cruises at a constant 65 meters per second in her 1500 kilogram BMW up Mount Soledad, which is inclined at 30.51 degrees. Part A, calculate V sub y. So you could draw a triangle and you know that the hypotenuse is 65. And V sub y is 65 sine of 30.51 degrees. Part B, calculate her instantaneous power. So power is delta W over delta T. So that's going to be mg delta H over delta T, because kinetic energy is constant. So the power is coming from the going up a height. And delta H over delta T is from part A. Question 8. Amber's 2,500 kilogram BMW accelerates from 8 meters per second to 5,200 meters per second in 4 seconds as it zooms up Pikes Peak, whose elevation is 72 meters and whose incline is 36.9 degrees. Part A, calculate the total work done by the engine. So we got the change in kinetic energy plus the change in GPE. So we have numbers for change in kinetic energy. We have numbers for change in GPE. Part B, calculate the average power for the entire trip. So the numerator is from part A, and the time is from the problem. It says 4 seconds. Part C, calculate V sub y 3 seconds into the trip. So V sub y initial is here. The acceleration we find. Then we could find a sub x and a sub y. For this problem, no need for a sub x, just a sub y. So we're going to use this equation. It's a Suvat equation. So a sub y is here. T is in the problem 3 seconds. And v sub y initial is here. Part D, calculate the instantaneous power 3 seconds after beginning to accelerate. Instantaneous power at 3 seconds. So there's going to be 3 steps. Step 1, calculate the speed of the BMW at 3 seconds. This is the speed of the BMW at 3 seconds. V sub y. This is V sub x. And this is V, the hypotenuse. Step 2, determine the driving force at 3 seconds. So sigma f sub y equals ma sub y equals f normal minus fg cosine theta is 0 newtons because the car is not jumping up and down. Sigma f sub x equals ma sub x equals f driving minus force of gravity sine theta. So let's solve for force driving, which is here. Step 3, use this equation. So F is from here. And then V is going to be 41 seconds from here. So this is our solution. Question 9. The takeoff thrust of an airplane engine is approximately 514,000 newtons. This airplane can reach a speed of approximately 247 meters per second. Calculate the power generated by the engine. So they gave us force of thrust and they gave us velocity. So that's all we need. Question 10. The height of the Burj Khalifa is approximately 830 meters. A man with a mass of 65 kilograms takes approximately 1,490 seconds to walk to the top of the building. Calculate the average power output. So that's going to be force of gravity because we're going up times the speed. They didn't give us the speed, but we know delta y over delta t. 830 meters divided by 1490 seconds. Question 11. A truck which has a mass of 1250 kilograms travels eastward on a horizontal road. There is a constant resistive force of 325 newtons. So it's a horizontal road. Calculate the power generated from the driving force when the truck has a speed of 12 meters per second and an acceleration of 0.625 meters over second squared. So step 1, use Newton's second law. Solve for the driving force. Step 2, use this equation, P equals FV. Part B, calculate the power of the constant resistive force. Well, P equals FV. Now force is the force of friction. Part C, calculate the time rate of change of the kinetic energy of the car. So it says time rate of change of the kinetic energy of the car. So that's kinetic energy over time. So that's delta KE over time. So we know this equation, and if we divide this equation both sides by time, we get power. We also know this equation. If we divide both sides by time, we get power. In our equation, theta is 0. So this actually just means here the power. So the net power we have is the solution. Question 12. A 15 kilogram box is pushed up a rough incline with an angle of 12 degrees with a constant speed of 1.25 meters per second. Part A, calculate the input power of the push. If the output power of the push is 255 watts with an efficiency of 25%. So efficiency times power in equals power out. So we're solving for power in. Part B, calculate the rate of increase of the gravitational potential energy of the box. Rate of increase, that means divided by time, of gravitational potential energy. So that's delta GPE over delta T, has units of power. So we were given M, we know G, we know delta H. It's going to be 1.25 times the sine of 12 degrees. Why? Because that's delta H over delta T. Part C, calculate the value of the resistive force acting on the box. So let's use one method here. Step 1, we could solve for force of push. Step 2, we're going to use this equation. Sigma F sub x equals force of push minus force of friction minus force of gravity. We know A sub x is 0 because it says constant speed. So solving for force of friction, we get this. And then we could solve for force of friction. Method 2, we know that the total work done is 0. And if we divide both sides by time, the total power done is 0. So we could just solve for force of friction to get 173. Question 13, a 70 kilogram man runs up an incline with a constant speed of 3.50 meters per second, which is 20 degrees above the horizontal. The constant resistive force acting on the man is 13.5 newtons. Part A, label the forces on the man. We got force of push, force normal, force friction, force gravity. If you want to call it the driving force, we could call it the driving force. Part B, calculate the power output of the man. Well, the man is moving at a constant speed. So sigma f sub x is equal to 0 since a sub x is 0. We could solve for force of push to get 248 newtons. Step 2, use the equation P equals FV. Part C, calculate the power done against the gravitational force. So that's just force of gravity times the vertical velocity. What's the vertical velocity? It's going to be 3.5 meters per second times the sine of 20 degrees. If you want to use a negative sign here, then that's okay. Question 14. An 85 kilogram car engine is attached to a massless chain and pulled across a rough horizontal surface which has an average friction force of 125 newtons and is 40 degrees above the horizontal. The car engine is pulled 625 meters in 5 minutes. Part A, label the forces on the engine. So we got this. Part B, determine the average value of the pulling force in which the engine moves at a constant speed. So this is Newton's second law of motion. Sigma F sub x equals force of pull cosine theta minus force of friction. This is a force of pull. It's pulled. Besides that, everything is good. Part C, calculate the work done on the car engine. Work is Fs cosine theta. So we determined F from part B. No. F is given to us. Because we know the acceleration is 0, the force of pull is equal to the force of friction. And because the force of pull equals the force of friction, we could just use the force of friction. Yes. Part D, calculate the power used to move the car engine. So power is E over T. We converted minutes to seconds. Question 15, a car starts from rest and accelerates at a constant rate in a straight line. The car experiences no friction. Draw a power versus time graph of the thrust force from the engine of the car. So F equals ma equals F thrust. P equals FV. So power increases at a constant rate just as V. So this is a linear graph. Question 16. A car starts from rest and accelerates at a constant rate in a straight line. The car experiences air friction. So the difference between question 15 and 16 is question 15 experienced no friction. Question 16, the car experiences friction. The magnitude of the air friction increases as the speed of the car increases. Draw a power versus time graph of the thrust force from the engine of the car. So remember, 15, it looks like this. Okay. Now remember, sigma F equals ma. Now we got force of thrust minus force of friction. We know as speed increases, force of friction increases. So if the term ma is constant here on the left-hand side, then F thrust must increase as force of friction increases. Remember, force of friction increases as the speed increases. So let's solve for force of thrust. The left-hand side will increase because force of friction increases, and ma has to be constant. So we have this equation here. Both force of thrust and V are increasing. So now we have something that looks like this. It's not linear. Question 17. An object of mass 2 kg is pulled upward from rest with a constant acceleration up to 6 meters per second in 3 seconds. Calculate the average power output of the pulling force. So, first we find a sub y, the acceleration vertically. Then we're going to use Newton's second law to find the pulling force. Then we can use P equals FV. And V is going to be V average. The average of 6 meters per second is 3 meters per second. So it says V average. Method 2, we could solve for a sub y. Then we could solve for y final. Then we could use this equation. Delta E sub k plus delta E sub p in the numerator. So delta H is this, and we know 1/2 mv final squared. And we're going to get the same solution from method 1 and method 2. Question 18. An electric motor has an input power of 400 watts. When doing work on an object, 250 watts of power is dissipated. Calculate the efficiency of the electric motor. Well, we were given everything. Question 19. 500 joules of energy is absorbed and 400 joules of energy is ejected in one cycle of a heat engine. Calculate the efficiency of the heat engine. So remember to be careful with the English language. The amount of energy wasted is 400 joules, so the amount of useful energy is 100 joules. Question 20. 455 joules of work is done in one cycle on a heat engine, while 825 joules of energy is wasted. Calculate the efficiency of the heat engine. So work in, we're going to sum 455 joules plus 825 joules. Question 21. A machine is supplied an amount Q of energy. The amount of useful work done is in the amount W, and the amount of energy wasted is R. State an equation for the efficiency of the machine in terms of Q, R, and W. So just remember, R is not in this equation. So that is something that might trick some students. Question 22. An elevator lifts a mass m up with a constant speed over a distance y. The efficiency of the machine is 20%. State an equation for the input energy of the elevator. So that's the equation. Question 23. The figure below shows an energy flow chart. State an equation for the efficiency of the system. So the efficiency of the system, we're going to have energy out, which is G, divided by energy in, which is X. So everything in the middle doesn't really matter. Question 24. An object is pulled up an incline with a constant speed by an electric motor. The efficiency of the electric motor is 0.655. The object gains 185 joules in GPE. Calculate the amount of energy dissipated. So be careful with the English language. Question 25. A solar panel has a surface area of 1.65 meters squared with an efficiency of 45%. The average intensity of radiation reaching the surface of the solar panel is 325 watts per meter squared. Calculate the average power output of 30 of these solar panels. So just plug in the numbers and that's the solution to get P out. Question 26. A first set of solar panels with an efficiency of 30% acquire an area of A. A second set of solar panels with an efficiency of 35% acquire an area B. Calculate the area of the second solar panels so both solar panels produce the same power output in the same conditions. So we should know that the answer is going to be less than 1. So 6/7, that's the ratio, because the second set of solar panels are more efficient. Question 27. Calculate the efficiency of an elevator motor with an input power of 1820 watts, which raises a mass of 355 kilograms vertically with a constant speed of 0.225 meters per second. So efficiency is power out over power in. We know P out is FV. We're going to use a force of gravity. And V is like delta H over delta T. Question 28. The efficiency of an elevator motor is 35% and its input power is 255 watts. Calculate the vertical height the elevator will raise a 25 kilogram object in 3.5 seconds. So you can see we're solving for delta y. Question 29. A 70 kilogram runner runs up an incline with a vertical height of 60 meters in 355 seconds with a constant speed. Calculate the efficiency of the runner if the power input of the runner is 175 watts.